Good morning. Let's get going. So we're looking at work and energy and solving problems. First, we looked at solving problems using our work kinetic energy theorem. Find the work done on an object by every force acting on the object. Set that net work done equal to the change in kinetic energy. That works pretty well. But I think most of us would prefer to take the energy approach, especially as our systems start to become more and more complicated. You have multiple masses, pulleys, springs. It becomes a little more complicated. But if you take the system approach with energy, we can tackle problems like that. So today we're gonna do this problem, our favorite problem, but we're gonna make it a little more interesting. We're gonna add a spring to it. Now our pulley is still massless, but in a couple of weeks, we're gonna tackle this problem again and the pulley is gonna have mass. But right now the pulley is still massless. We've got M1 and M2, I should write that here somewhere, massless pulley. So if we're given all the information, the coefficients of friction, the angle, the masses, the spring constant, all that stuff, we want to find, and the initial velocity, we release this thing from rest, and the spring is at its equilibrium position when we release it. M2 starts to go down, down, M1 starts to go up, and we want to know the velocity of M2 the split second before it hits the ground. Before we got to energy, we wouldn't be able to solve this problem because the spring is a force that changes over time, changes over the distance. That means the acceleration of our blocks is not constant anymore, it's changing. We can't just use Newton's laws to find the acceleration because we'd only be finding it at one instant. And then that wouldn't work in a kinematics equation. So as soon as you see the spring in there, you should be thinking energy, unless I'm asking for the instantaneous acceleration, I guess, then you could use Newton's laws to find the acceleration at that instant, but it's not going to help you find the final velocity. So there's our picture, and what I want you to do is fill out an energy bar chart. See, as our system becomes more complicated, you can see the energy bar chart is kind of helpful. I like to do it, do it for the first week. As you crank out problems, draw the energy bar charts. After that, you can decide whether you like them or not. But I think it helps get your mind thinking the right way about energy equation. You want to get that equation correct. So first, what do we have to do before we can fill out that energy bar chart? Yeah, that's not the first thing we need, though. We are going to need to define our heights. Free body diagrams are always a good idea, but actually, I'm not sure they're going to help you here. You'll need them eventually. If you're trying to find, like, for example, you're going to need it to get the normal force so you can know the friction force, things like that. So free body diagrams are not a bad idea. We should probably do them just for practice. I'm not sure you need them right off the bat here. System schema, why is that? Because we need to define our system. That's what we need to define. We need to define our system. And so I like to draw the system schema because it gives me a visual, right, of what's going on in my system. So if I did, where would I do my system schema? I'm going to squeeze it in. I'm going to move this down, I think. So what do I have? I've got M1. I've got a rope. I've got M2. See how I kind of draw my objects sort of in the same orientation that they are in my physical problem. And then what else is there? There's a spring over here and the earth. Is that everything? I think that's everything. So I have both ends of my rope in the system. So I can just draw the whole rope in there. The rope is not going to affect anything. You can't, I like to say, you can't make your car go faster by pushing on the dashboard when you're sitting in the car, right? Those are internal forces. They're not going to change the motion of the system. So because the whole rope is in my system, it's pulling on one and pulling on the other. It's just the effects are canceling out in terms of the whole motion of the system. But if you only have one end of a rope in your system and one end is out being pulled or doing something else, then that is affecting your system. You have to account for that. So here I have it, it's in my system, M1, the rope, that's a contact force, they're touching each other. The rope with M2, a contact force, they're touching each other. M1 in the spring, got a contact force there. What do I need now? I need M1 in the earth. M1 is in contact with the earth. I kind of like to draw a double arrow because we break up the contact force into a normal force and a friction force. So I draw this double-sided arrow to indicate that I'm going to have, in my free body diagram, I'm going to have two vectors there, not one. And then it can interact with the earth through gravity, right? Non-contact gravity. There's only one non-contact force we have this quarter, gravity. M2 is not touching the earth, but it does interact through gravity. And I guess the spring is touching the earth, but we don't really care about that one, but I'll go ahead and put it in there. Did I get everything? I think that's good. Okay, so I will define the system. This is how I would normally do it. I would want to include the spring in my system because we have potential energy, and potential energy is usually the easier way to deal with it. And I'm going to include the earth in my system because I have potential energy for gravitational potential energy, so I can account for changes in elevation that way. So it's usually best to try to include things in your system. I will draw my system boundary like that. So now we can fill in the energy bar chart because we know what's in our system and what isn't. When we have transfers of energy within the system, we account for that with potential energy. If we have something reaching into our system, we account for that with work done by the external force. So first we're going to do this problem with this definition of the system boundary, and then I'm going to change the definition of the system boundary, and we'll set it up again with the new definition. Now, I went ahead and did this last night because I knew my energy bar chart's getting longer, right? My energy equation's getting longer because I've got a spring in my system. I've got two different masses. And if I have two different masses, I've got kinetic energy for both of them, right? Kinetic energy for one, kinetic energy for two. And both of them could be going up and down. I've got a potential energy for one and a potential energy for two. I've got my spring. My energy equation is kind of stretching out. If I had a second spring in the system, I'd add a U spring 2 over here, right? I would just add terms to accommodate what's in my system. So I knew I would get a little messy if I tried to do this by hand. So I typed it up last night, but this is our equation. I think I've accounted for everything here. Now I only have one friction force right here. I only have one friction force because I only have one friction force in my system. Only M1 is sliding. If M2, if my other angle, if it was a 2, instead of being a cliff at the end of my incline, if it was another incline and both of the masses were sliding, I would have 2 friction forces, right? A work done by friction on block 1 and a work done by friction on block 2. I would just add a second one here. But I only have one, so I just left it that way. So go ahead and fill in the bar chart as best you can. And then we'll talk about each term. Just to review, we're given all the masses, the spring constant, the angle, all of that stuff, and the fact that it starts from rest at the equilibrium position of the spring. The spring is not stretched or compressed at the beginning, but at the end, the spring is stretched, right? The spring gets stretched as M1 moves up the incline and M2 falls down toward the ground. Okay, let's go through it. So we'll start with kinetic energy. M1, is it moving at the beginning? No, that's given in the problem. It starts from rest. M1 and M2 are connected by a string, so they have to have the same velocity all the time. Neither one of them is moving at the beginning. So I'll put a 0 there and a 0 there. And at the end, are they moving? Yes, they're both moving. They'll have kinetic energy. If they're moving, they have kinetic energy, and kinetic energy always positive. So some positive amount of kinetic energy for both of them. I don't know which one's bigger. Depends on the mass, right? Potential energy, gravitational potential energy for block 1. Does block 1 go up or down? Yes, it does. It goes up. So let's most of us like to call the lowest point in the problem 0. So block 1 starts right here. And it ends up here somewhere, right? Oops, not Y2. Y1 final. Okay, it ends up here somewhere. So it has to, the final has to be more than the initial. Let's call one of them 0. Usually we like the lowest to be 0. I would call this one 0. And then at the end, it has to have more than 0, which is some positive amount. Yeah, we'll fill it in a minute. Okay, block 2. Does block 2 go up or down? Yes, it does. It ends up at the end lower than where it started. So it has to, at the end, it has to have less potential energy than it started with. So let's call the end 0. We don't have to. If we call the beginning 0, then the end would have to be negative. Let's call the end 0. Then it has to have started out with something more than 0, which is some positive amount. So if it ends up at 0 and it started higher than that, it had to be a positive amount here. Is our spring stretched or, so we're calling this y2 equals 0, right? We're picking a different 0 for mass 2 than we picked for mass 1. That's okay. All we care about are changes in height. All we care about are changes. So it doesn't matter where 0 is defined. Spring potential energy. Is our spring stretched or compressed at the beginning? No, it's at its equilibrium position, not stretched, not compressed. So it has no energy stored in it at the beginning of this problem. Is our spring stretched or compressed at the end? Yes, it's stretched at the end. Do we care whether it's stretched or compressed for potential energy? No. If it's stretched, it has energy stored. If it's compressed, it has energy stored. Spring potential energy, always positive. As long as it's stretched or compressed, it's got energy. Spring potential energy, always positive. Friction. Is there friction? Yes, there is. We have one friction force acting on block 1. Friction force will do negative work. And do we have any external forces? No, nothing reaching in, nothing crossing that boundary. No external forces, so there's no work done by external forces. So now we need to come up with our equation. This is just a tool. The energy bar chart is just a tool to help us get the equation right. So I've got M2G H. That's this one right here. Right, I've got here 0, 0, 0, M2GH, 0. Now I've got some negative quantity. Work done by friction is the friction force times the distance. Friction force, actually, let me write it out as mu times the normal force is the friction force times the distance. What distance does block 1 slide up the incline? H. So that's that. I have another 0. Now I have my equal sign. And now I add up all the energy at the end. Oh, I've got a lot at the end, don't I? I've got a 1/2 M1 V1 final squared. That's this term right here. Now I have a 1/2 M2 V2 final squared. That's this one right here. I'm running out of colors. Oh, H. Why is it H? So M2 drops by a distance H. So that means that this distance is H. So we are looking at the distance that the friction force acts on block 1, which is the distance along the incline. I think you're getting ahead of me. You're thinking about the height. We'll get to that in just a second. And now we have a UG1. So this is going to be plus M1G. Now I'm going to call this, what am I going to call this? Well, I'll just fill it in what it is. It's Y1 final. This is the height. We need this here, right? Y1 final. Let's draw it over here. So our box goes up. This is H. This is Y1 final. This is theta. So Y1 final is H sine theta. Okay, I think that was the question for the previous one. So that's this one. Now we have a 0, and now we have a plus 1/2 K H squared. Because what's the distance the spring is stretched? It's the distance block 1 moved up the incline, H. So there's our equation. We plug in what we know. Hopefully there's only one unknown. We solve for that unknown. V final. So I don't have to call this V1 final and V2 final. They're the same. I could just call it V final. I'll write that here. V1 final equals V2 final equals V final. Normal force, you have to find the normal force. Yeah, we do know the normal force. Normal force is going to be, so this is for, and then the normal force is going to be M1G cos theta, right? So this is where somebody mentioned earlier drawing free body diagrams. This is where free body diagrams would be helpful. You need to figure out your normal force, things like that. But really, we're not looking at forces so much here unless we're thinking about what kind of work they're doing. I guess we are thinking about it in that sense. But not quite as helpful here unless they help you see the big picture and what direction things are going and finding normal forces for friction. Okay, let's see, there was a question. You can call it whatever you want. H, Y, call it whatever you want. I already used an H. See, don't use the same symbol for two different things, right? I already used an H for the height, the starting height of block 2. I should have called that something else. I should have called it D or something, but I called it H. So when I went to look at block 1, how much it went up, normally I would call that H, the height that it changed. But I already used an H somewhere else in my problem, so I didn't want to get confused. So I called it Y, delta Y, Y final, something else. Maybe I should have used a D or something over here instead of an H, and then I would have used H for the height of 1. But call it whatever you want so that you know what it is and you don't get it confused with something else that's different. Spring force being negative. Spring force, I almost never use negative spring force. I almost never treat it like a vector. I just look at I get the direction from the situation, and then I define whether it's positive or negative. So if I draw a free body diagram for my block 1, as it's moving, once it starts to move up the incline, what do we have? We have a tension, we have a spring force, we have M1G sine theta, M1G cos theta, we have a normal force. Anything else? What's happening here? M1, we got a normal force. Did I get friction? Oh, no, I didn't. I'm running out of room here. Friction force, normal force, friction force, tension, gravity. I think that's everything. So as the block is moving up the incline, I know my spring force is down the incline. Now, if I want to call that the negative direction, it's in the negative, it's negative. If I want to call that the positive direction, it's positive. But I'm not using Newton's laws at this point. If I wanted to find the acceleration at this instant, what's the acceleration? Then I would define a positive direction and call my spring force positive or negative depending on what my positive direction is. But in this case, we're using spring potential energy. Spring potential energy is always positive, 1/2 kx squared. And if we did the work done by the spring, work done by the spring as an external force, which we will do next, then you'll see you have to decide whether it's doing positive work or negative work. But we will do that next. That's a good lead in to where we're going. Excellent. Okay, so let's do it again. Same problem. With a different system definition. We had M1, we had the rope, M2, the spring, and the earth. M1 was interacting with the rope, of course. The rope was interacting with M2. The spring and M1 are interacting. M1 and the earth, non-contact. M1 and the earth, contact. I'm just copying this over. This is the exact same. M1 and the earth, non-contact. M1 and the earth, contact. M1 and the earth, contact. M1 and the earth, non-contact. M1 and the earth, contact. 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 M1 and the earth, conta system schema I had earlier. We don't really care. The spring is interacting with the earth. We don't really care. Okay, so this is exactly the same as what I had earlier. I'm just recopying it. But my system definition is going to be different. I'm going to use this as my system. Now, I'm going to fill in my bar chart. So think about what we have here. I've already, what do I have? I've got an external force reaching in right here. I've got an external force here and here. And I'm treating this one, I don't need to worry about, right? Because one of these lines, one of these is gravity, one of these is normal force, and normal force doesn't do anything, doesn't do any work in this problem, right? The other one is friction, and I account for friction separately. I've got friction is over here, so it doesn't matter. Friction, it doesn't really matter whether it's internal or external. I always account for it by itself. So I have three forces that are reaching into my system now that I have to account for. So I've changed my energy bar chart a little bit to include three external forces, whereas before we didn't have any. So go ahead, try to fill that in. I'll give you a minute. Should we go through it together? We'll start with kinetic energy. Anything moving at the beginning? No. So no kinetic energy, block 1 or block 2. Are they moving at the end? Yes. Then they have kinetic energy. Kinetic energy, always positive. Gravitational potential energy for block 1. We don't have any because the Earth is not in our system. So we cannot have gravitational potential energy. Spring potential energy. We can't have any because the spring is not in our system. The item has to be in the system to have potential energy. Work done by friction, that we have. That's always negative. Now our spring is reaching into the system and doing work on the system, on M1. What kind of work is it doing? Positive or negative? Negative. Because, where's our picture? As M1 starts to go up the hill, the spring becomes stretched. It's pulling back. M1 is going up the hill. The spring is pulling down the hill. So it's doing negative work. It's trying to slow down block M1, doing negative work on M1. The work done by a spring could be positive or negative, but spring potential energy is always positive. Work done by gravity on block 1. Block 1 is going up the incline, so gravity is pulling down, doing negative work, trying to slow down block 1. Work done by gravity on block 2, positive, because block 2 is dropping, gravity is pulling down, doing positive work, trying to increase the speed of M2. Now we write our equation. What do we have? Negative equation. The spring does negative work. If we don't include the spring in our system, we can't have potential energy. We have to account for it as an external force. See, this is the trick, the pitfall that students fall into. They'll say, "Oh, my block goes up, so it has a potential energy, mgh," and then they'll say, "But gravity did work on it, mgh, amount of work on it." They'll double count the effect. It's one or the other. If the Earth is part of your system, you have potential energy accounting for the changes in height, but gravity doesn't do work on it because it's in the system now. It's not an external force. If the Earth is outside of your system, you can't have potential energy. That's only for things in your system. But how do you account for the effect of gravity? You say it's an external force reaching in doing work on the system. Same with the spring. So if the spring is in the system, we have U spring, but it does no work done by the external force of a spring. If it's out of the system, we don't have U spring, but we have work done by the external force there. And if it's in the system and you're dealing with U spring, potential energy of the spring, then it's always positive. It'll show up on the correct side of the equation. You always put it as a positive number. If it's work done by the spring, you have to figure out whether it's doing positive work or negative work and get the sign correct. It could be either one. Friction is going to be mu times my normal force times the distance it falls. That's that term right there. Then I've got negative work done by the spring. What is that? 1/2 K H squared. Then I've got negative work done by gravity. That's mg h sine theta. Right, that's y1 final. You see how it might have been easy to forget one of those negative signs if you didn't have the bar chart there to kind of prompt you, oh, wait, this is negative, this is negative, this is negative. Plus M2, this is an M1, 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 this is an M2 GH. Then we have our equal sign, and then a 1/2 M1 V final squared, and a 1/2 M2 V final squared. Those are these two terms right here. Yes, they're all the same. Question is that this equation looks like the work kinetic energy theorem. Can you just use that directly? Absolutely, they're all the same. Work kinetic energy theorem ends up giving you the same equation as the conservation of energy, but I think most people find it easier to think about conservation of energy. There's a lot going on in this equation. Think so as your system becomes, when it's just one, when your system is just one thing, a block sliding down an incline, work kinetic energy theorem, conservation of energy, they just immediately both give you the same equation. But when you have two masses and a pulley and a spring, maybe two springs, it becomes more complicated. And I think conservation of energy is an easier way to picture what's going on. Most people like it better. In the end, all of these give you the exact same equation. It's just the term is on one side of the equation instead of the other side of the equation, things like that. Okay. The normal force is mg cosine theta. And then the height, this is the distance. This is the distance. That's F. Okay. Now, the applications of this all around us, we use this stuff all the time, mostly for transferring energy, right? We turn one type of energy into another type. Generating energy involves transfer from one type to another. We can take energy that comes to us from the sun in the form of light, and we can change that into heat or electrical energy. We can take potential energy, water that's high up, it has potential energy. We can build a dam and allow that water to come down, turn a turbine, use its energy of potential energy to turn a turbine. That turns it into mechanical energy, and that turning turbine, we can convert that into electrical energy. You'll learn about that in physics 4b. So we're transferring energy from one type to another. We do that all the time. Your car starts up, right? There's chemical energy stored in the gasoline. You burn that, you get that chemical energy, turns to heat. That heat we use to turn into mechanical energy to make your car go. Then you use the brake pad, turns that mechanical energy, your car is moving, kinetic energy, turns it back into heat, dissipates that energy as heat. Runaway truck ramps, you see these if you go down I-5, driving to Southern California, going over the Grapevine, runaway truck ramps. The idea there is a truck, if the brakes fail on a truck, lots of weight pulling it down the hill, lots of potential energy. It's going faster and faster and faster as it comes down the hill. Its brakes have failed. So we need a way to dissipate all that energy. How does that work? Well, you have to convert it to other forms. So they have this soft gravel there. As the truck plows through the soft gravel, the gravel is moved and it heats up a little bit and it dissipates a lot of the energy. Sometimes they build a ramp so that gravity, some of that potential, some of that speed, kinetic energy gets converted into gravitational potential energy. It goes up the ramp, but it's a way of dissipating that excess energy. But you want to continue to think about it, like everything in this class, as a physics student, right? You think in terms of, we use terms in everyday usage that are not exactly correct in physics class. And one of those was like work done. Remember, go to the gym, you lift the weights, you leave, you haven't done any work, because work has to be done on something. And if work is done on that thing's energy had to have changed, right? Work tells us change in energy. If you went to the gym and all the weights are in the rack and they're not moving, and you leave and all the weights are in the rack and they're not moving, you haven't done work on anything. No net work was done. Now, internally in your body, that's a different story. You have to think like a biologist in biology class, and what's happening inside your body. Things are happening, lots of stuff is happening. Your muscles are using lots of energy and things like that. We don't care about that in physics class. Work is change in energy, and get in the habit of thinking of work done by some force on some object, right? Work done by the string on the box, work done by gravity on the box, work done by my hand on the box, right? That kind of thing. Think in terms of those words. And if you always say it that way, then that'll help you. And if work is done on that object's energy had to have changed. If its speed would increase because of that force, the work done on that object is positive. If the speed would decrease, the work done is negative. So you kind of have to think about, if this was the only force acting on the object, would it be causing the speed to increase or decrease? That helps you too. But you should be able to get it from the directions. If the force has some component in the direction of motion, it's doing positive work. If it has some component opposite the direction of motion, it's doing negative work. So practice this a little bit. Use the energy bar charts. Think about how you're defining your system so you don't double count the effects of things. And practice with the energy bar chart. In the end, you don't need an energy bar chart, right? It's like training wheels. But in the beginning, I think it's nice, and it kind of gets you thinking the right way about this equation and helps you get your signs right. So we'll end it here. We'll start with momentum next week. Momentum. Energy and momentum go really nicely together, because in spots where we can't use energy to solve a problem, typically we can use momentum. They complement each other very nicely. So we'll start with that next week. We'll stick around if you want to do a review session. We can do that. I'm just going to take a little break here, 10 minutes. We'll start our review session at noon. Okay? Otherwise, have a good weekend.